Scientists argue the first spark of life on Earth didn't start here. Instead, it survived a treacherous journey through space, encased inside a Martian meteorite. Look at Mars today. It's an entirely barren, irradiated desert without a single drop of liquid water on its surface. But this animation of the early solar system shows a completely inverted reality. While a newly formed Earth was still a boiling, toxic furnace, Mars had a massive evolutionary advantage. Because it's smaller and further from the sun, it cooled down much faster. That rapid drop in temperature allowed freshwater oceans to pool across the Martian crust. Millions of years before Earth was even habitable, microscopic bacteria were already spawning in those alien seas. If Mars had millions of years of a head start, with perfect biological conditions, we have to ask what stripped that world of its oceans and left it dead, while Earth somehow inherited a thriving biosphere. The destruction of Mars began from above. A massive barrage of asteroids slammed into the planet, delivering kinetic force equal to thousands of nuclear detonations. That sheer kinetic impact instantly vaporized the upper layers of the Martian crust. The microscopic ecosystems pooling in the surface water were completely incinerated. While Mars was being sterilized, Earth suffered its own cosmic collision. A rogue planetary body smashed directly into our world, shattering the crust and tossing out a massive ring of debris that eventually fused into our moon. This diagram shows the critical result of that impact. The massive gravitational pull of the newly formed moon acts as an invisible tether, locking Earth onto a very specific, stable axial tilt. As Earth orbits the sun, that continuous tilt ensures one hemisphere gets more direct sunlight than the other, alternating throughout the year. This specific mechanism drives regular, predictable seasons and stops the planet from suffering wild temperature extremes. Cosmic debris fields do not target planets with intent. The exact same type of random, kinetic violence that wiped out the first spark of life on Mars accidentally gave Earth the mechanical stability needed to keep oceans liquid. Mars did get one brief opportunity to recover. Subsurface ice began melting when massive volcanoes erupted. To understand the scale of those eruptions, look at the Himalayas. Mars's Olympus Mons is 3 times taller than Mount Everest. Volcanic steam formed clouds, and rain fell on Mars once more. But the planet's extreme distance from the sun was a fatal flaw. The global temperature plummeted, permanently freezing the remaining surface water into solid ice and killing off whatever microorganisms had clung to life. Back on Earth, newly stabilized temperatures allowed early oceans to thrive. Heat-resistant bacteria began multiplying rapidly, and as a byproduct of their digestion, they pumped massive amounts of oxygen into the sky. This diagram shows exactly how that atmospheric chemistry evolved. When lethal ultraviolet radiation from the sun struck these rising oxygen molecules, the energy split them apart. They instantly restructured into O3, a dense layer of ozone. Wrapping entirely around the globe, this new layer absorbed incoming UV waves. Only after that protective canopy was completely formed was it safe enough for organisms to crawl out of the oceans and survive on dry land. Having oceans of liquid water is useless if space itself is constantly microwaving the surface. Without a specialized, naturally occurring atmospheric shield, radiation makes terrestrial biology impossible. Millions of years later, Earth was dominated by massive reptiles. Giant dinosaurs occupied every major ecological niche, comfortably ruling the planet for 160 million years. Their reign ended abruptly when a 6-mile-wide asteroid struck the Yucatan Peninsula. The impact ignited global firestorms and choked the atmosphere with ash, plunging the Earth into thousands of years of unbearable, toxic climates. The total starvation of those massive apex predators left vast ecological spaces completely empty. Small, warm-blooded mammals that could hide underground suddenly had the food and territory required to multiply. Over the next 60 million years, those surviving mammalian species underwent a chain reaction of physical adaptations. They grew larger, developed complex brains, learned to stand upright, and eventually began using tools. Our entire species exists as a direct byproduct of an orbital strike. If a giant rock had missed Earth by even a few degrees, giant reptiles would have kept eating our ancestors, and human intellect would never have evolved. Biological existence demands an incredibly strict set of conditions. A planet needs the exact right distance from a star for liquid water, a heavy moon to stabilize its tilt, an ozone layer to block radiation, and a magnetic core to deflect solar winds. Despite benefiting from this rare planetary alignment, our continued survival is entirely fragile. Today, humans possess the technological capacity to instantly trigger a mass extinction of our own making, either through biological warfare or through the detonation of nuclear arsenals. Even if humanity does completely destroy itself, the billions of years of fossil records prove that the planet will survive. Basic cellular life is incredibly resilient, and it will simply adapt, mutate, and replace us with something else over time. But there is one inescapable threat that will permanently wipe this planet clean. The nuclear fusion engine powering our sun is slowly running out of fuel. As that hydrogen fuel depletes, the sun's outer layers will swell. It will eventually expand by 15%, generating enough heat to boil away Earth's oceans into space, before engulfing the rocky crust entirely. Every physical planet in the universe has a definitive expiration date. When you look at the silent, irradiated dust of Mars and compare it to our vibrant blue oceans, it proves that our brief window of existence here is an incredibly lucky, highly temporary anomaly.